They asked us to take pictures, and since the is quite new of the workshop, I hope everyone is fine with that. With us taking pictures. If not, if you don't want to appear or anything, just let me know. And let me start the lecture.
So hello, so good morning. So let me recall what we said last time. We used classical Galois theory. Plus results from algebraic group theory. To prove some kind of Ax-Lindemann theorem for the exponential. Okay, and this strategy works in for other functions too, for other solutions of linear differential equation, and the other also version for abelian varieties. But so what I want to describe today is a modification of classical Galois theory, which allows to replace Ax-Lindemann here by Ax-Schaunel type of result, where the function you consider are not necessarily rational functions, but power series. And so one of the things that we learned from the classical setting is that if you were starting with a vector-valued linear differential equation, we were immediately looking for a fundamental system of solution. Not one solution, but a fundamental system of solution. Okay, and this means that instead of working with vector bundles with linear connections, with a flat linear connection, we will instead work with principal bundles with a flat principal connection. Okay, so the first thing I will do is introduce some vocabulary about this kind of objects. So I'm sure many of you are very familiar with the vocabulary, but I will recall it anyway. So first, we are going to fix. So we have a map from P to X, where X and P are smooth complex varieties. And P is a submersion. Okay, so for the moment, I have no D structure, no action of G on P will come later. And so we have an exact sequence of vector bundles on P. So we have TP, which is sent to the derivative of P to the pullback of X, that I will send like that. And the kernel is a set of vertical vectors, and it's called TP over X. Okay, so what is a connection? A regular connection is a splitting of this exact sequence. Okay, namely, you can give it in two different ways. Both ways are useful to think about, so I will give you the two ways of thinking about it. First, you can think about it as a subvector bundle of TP such that when you look at TP, this is a direct sum of H delta plus TP over X. Okay, and equivalently, this is also a section of DP, namely a map morphism of vector bundles. Delta, which takes a vector in X and over the same point of X, a point in P, and lifts this vector into a vector in P. Okay, and such that, so we will denote it V and P, you associate delta Vp, such that, so this is a section of dp, so if you take dp of delta of Vp, this is equal to V. Okay, so these two data are essentially equivalent, are completely equivalent. If you get one, you get the other. If you take the other, you get one. And from this, from a delta, from a connection delta, how? Oh, you're right. Vp. No, no, this is for vectors, right? Oh, you're right. This should be, yeah, you're right. So, yes. So times P of PP. Yeah. So from a connection delta, you get a lifting operator. So that I still denote it by delta, which takes a vector field on X and sends to a vector field on P minus 1 of X. And we do the same thing. So if you take a vector field in X, what you do is that you apply. So you have you take get the vector which to P. So associate the vector delta V of P of P. Okay, and which is a vector on P, which lives in P minus 1. And so saying that this connection is flat, if equivalency. Okay. So H delta is a regular foliation. Okay, so what I mean is that the distribution given by H delta is stable by the Lie bracket, or you can view it on the lifting operator if V and W so if you take any two vectors on V and you compute the bracket of the vectors, this is delta of the bracket of the vectors. Okay. So notation for every P. So you see if I write here. So for P in P, we denote by LP the leaf of H delta through P. Okay, and so you have, if you restrict the projection from X, the property that H delta is a complement of T of Px tells you that this is a local isomorphism at every point P of L, at every point of LP. Okay. But in general, it's not surjective. In general, not surjective. Okay, because you can just take some points of P out, even if it's surjective first, you just take a point of P out. Okay, so now let me add the G structure. So assume now that this is a G principal bundle. Okay, so what does that mean? So this means that we have an action of G on P, and we are going to take the action on the right. I don't really think it matters. So which to P, okay, so which to PG associate P times G. Okay. Yes. Okay, the leaf of a folio. Hmm?
What do you mean by local isomorphism?
If it, but it's local, right? So locally it's not dense. So look, I mean, this is something that looks like, and that project on a.
It's in the hidden analytic category. So it's local by holomorph. There is mobile, which is epsilon. Not the same thing as Calum. It's the same thing as Calum. But Calum was in the algebraic category, but when we spoke about leaves, we were in the analytic category. We don't speak about leaves in the algebraic category.
So I think about it as an immersed analytic subvariety.
Yeah,
Okay, but here everything is regular, right? So everything is very naive somehow. Okay. Okay. And so we have this action such that so it commutes with P, and the fibers are principal homogeneous spaces under the action of G. So the way to write it down is that the morphism from P times G to P times XP, which to P G sends P point G, is well defined as a morphism. Okay, this is a shortcut for saying that the fibers are principal homogeneous spaces under the action of G, and that G preserves pi. Okay, so now we say that the connection is principal. If equivalently, so the following thing happens, either when you think about H delta, so if you take, so this I will denote it by Rg of P. Okay, so if you look at Rg and you pull back your foliation H delta, you get H delta. The foliation is stable by the action of G for all G and G. So you can also view it on the operator that I defined here. So if you want to compute delta V at the point Rg of P, Okay, you just have to take the derivative of Rg and to apply it to delta V at the point P. Okay, and the third possibility is that for every leaf LP, if you look at the leaf through G times P, this is G times the leaf of P. Okay, so I finished with the definition. But you see that, so compared to this situation that I described here, the leaf LP is always surjective, project surjectively on X. This comes from this property. You can see that actually you cannot have removed point from P. Okay, here. Okay, P from LP to X is an unramified. Analytic. Okay, so now we want to define the Galois group of such an object. Okay, but first let me give you an example. We'll see more example in the next lecture, if it's enough. But an example which is related to linear equation. In the direct sum. No, it's in the algebraic category, the direct sum.
This is in the algebraic.
Yes. Okay, so let me give you an example that will explain you how to define the Galois group. So if I start again with a linear differential equation, okay, I can look, so where A of X might be of X. I can look at pi, which is so from P, which is so A1 times GLP, see, to A1, and which, so I will denote the coordinate by X, Y, I, J sends to X. And, okay, and the connect, so this is a principal bundle by definition on the action on the right, and the connection is given by delta. So if you take the vector lambda over d over dx at the point X, okay, you send it to lambda d over dx plus the sum over aj that you apply the matrix A of X at the point Y. Let me denote it by big Y. Okay, and you do d over dy. Okay. And you see that this is right invariant, somehow vector field plus this form. Okay, so this is a principal connection, is a principal connection. Outside is a regular principal connection. Outside of the poles of A of X. Okay, and where is the flatness condition? But there's no flatness condition because this is one-dimensional. Okay. So if you see if you remember what we did last time, okay, if you have P of X. On X, you have the vector field d over dx. Okay, X is A1. Okay, and you can lift it using this connection to delta d over dx. Okay, and if you look at the generic fiber, okay, its coordinate ring is what I denoted R0 last time. This is so if this is a C of X, where you take the Yij and you inverse the determinant. Okay. And the derivation induced by this vector field on this coordinate ring is the derivation delta 0. Okay. And delta 0 that I defined last time is the derivation induced by delta derivative. Okay, so what we were doing for defining the Galois group, the PV ring in that case, is that we were taking a maximal differential ideal in this differential ring. Okay. And so what are we going to do for a connection to define the Galois group? We are going to pick Z, a minimal delta invariant subvariety. So the fact that the ideal is maximal tells you that the variety, so of course a non-empty minimal delta invariant subvariety, closed subvariety, and define that gal of let's say Z is the set of G in G, such that Z point G is equal to Z. Okay, so this is the idea. Okay, which correspond exactly. You see that if I do that, I will get exactly, in this example, I will recover the classical theory. Okay, so let me make some remarks about this object. So we want to make sense of that in a bit more precise way. And so I think, I write it like observations. So the first observation, from which everything follows, is that, okay, the following are, so if you take, let Z included in P a closed subvariety, the following are equivalent. First, Z is a minimal delta invariant subvariety. The second thing is that Z is the Zariski closure of a leaf at some or any point in Z. Okay, so I gathered three equivalents in two statements. So either at some point or at any point, okay, this will give you that Z is a minimal delta invariant subvariety. Everything here is equivalent. Okay, so this is obvious. And so the observation two is that from this, you can deduce easily that if Z is a minimal delta invariant subvariety, then Z is a gal Z principal Mendel. Okay, so we know what the minimal delta invariant subvariety look like. It could be that this group is very small, actually. Okay, but this tells you that indeed this group is not that small. If you take any minimal delta invariant subvariety, the group G, there's many elements with which preserve the subvariety Z. You want me to prove that, or is it fine? Okay, so you want to prove, let me just, you want to prove that if you take So this is, you just use the first part. Okay, so you have this isomorphism between P times G and P times XP. So you want to see that it restricts to an isomorphism from Z times gal Z to here. So clearly, if you take a point in Z and a point in gal Z, by definition, it preserves all Z. Okay, so it will send it to Z times XZ. Okay, so what you want to show is that if PQ are 2 points are in here, okay, you can find an element of the Galois group of Z such that they are conjugate by this element. Okay, we want to show that this is an isomorphism. This is what we want to do. So what are we going to do? We know that there's a point in G. So there exists G in G such that Q is equal to P of G. But now you see that G, ZG intersected with Z, okay, is non-empty. This is a delta invariant subvariety. Since the connection is principal, this is a delta invariant subvariety. Okay, but by minimality of Z. Okay, ZG is equal to Z, which implies that G is in gal Z. Okay. Okay, so now that we have done this, the third observation before defining the Galois group entirely, that's what happens if you change Z. So the observation 3 is that if Z prime is another delta invariant minimal subvariety, then Z prime is equal to Z, so G times Z, Z times G, and the Galois group of Z prime is a conjugate. So I don't know where to put the -1. Okay, it's plus or -1 of the Galois group of Z. Okay, so we are exactly like in the situation. The Galois group is defined up to conjugation. Okay, and so we define the Galois group of delta to be gal Z for some delta invariant, some minimal delta invariant subvariety. Okay, and this is well defined up to conjugation. Okay. So this is just because the foliation is G invariant. So if you take a leaf, so this is again by observation 1, you can think about both of them as a leaf. The two leaves are projecting surjectively on X. Okay, so you can take a point on X and the two leaves, the points over the two leaves above. G acts transitively, so you have that one is LP and the other one is LGP. And so you get exactly that Z prime is equal to ZG. Okay. And this follows from this. Okay. And so in the linear example, the Galois group of the connection is the Galois group that we defined before. Okay. So now I want to explain the general transcendence result in this setting about a principal connection. So my setup will be the following. So you're given, you're fixing a map from P to X, so a G principal bundle. Okay, I'm going to assume that G is connected. So G is a connected group. Delta, a flat principal connection. So flatness will come into play soon. I'm not sure where I use it here. Okay. And we assume that this connection has maximal Galois group. That's gal of delta is equal to G. Okay, so you have a principal bundle, a flat principal connection on this bundle, and with full Galois group. Okay. So the definition is that if you take Y including in X a closed subvariety, okay, we say that Y is delta special if the Galois group of the connection restricted to Y is a proper algebraic subgroup of gal delta is equal to G. So delta special subvariety is a subvariety such that the Galois group drops. Okay, but you see that here I have cheated a little bit because I've defined everything when X is smooth. Okay, and here Y doesn't have to be reducible. So to be precise, you have to ask that for every reducible component of Y, on the smooth locus of this reducible component, this Galois group is a proper algebraic subgroup. Okay, the theory here is local on X. Okay, if you replace X by a Zariski open set, you don't change the Galois group of the connection. And so you just take that the restriction of delta to the smooth locus of Y has this property. Okay. Special. Okay, if the Galois group drops. And so, oh, it's nabla. Yeah, sorry. Yeah, it's nabla in the other direction. Okay, and now I can state the transcendence result from which all the other transcendence results will be obtained. And then I will start to give a proof. I don't know if I have time to finish the proof.
How should you think about this nabla special?
So the definition. So okay, so this is, so for example, we try to give an example. I think this is correct. Is that what happens? So if you take GM times GM, you want to check for the exponential. And so I'm going to give, so you look at the principal, so you look at Y prime is equal to Y. This is a linear equation and over order 1, and you look at a principal bundle over A1. Okay, X is A1 here. Okay, with this as a principal connection. Okay, this is just a full. Then you look at the product of two of them. So you have X times X, which is A1 times A1. And here you have a principal bundle, which is GM times GM times X times X. Okay. So what are the special subvarieties in X? They are actually the line. They are the line of the form. So sum of EI XI is in C. So the connection corresponding to this equation. And then when I give the connection here, I have a unique connection on the product coming from the product of the connections. So here I'm looking at the connection which was given by the, when you have a linear equation, you get the connection associated to it. So here it's particularly simple because it's here. I look at the product of the two. Okay, this is to relate to what we've done last time. And so here a special subvarieties. So this is sum of EI. So this is A1 to A1 with coordinate X and Y. And if I look at an equation of the form Cx plus dy is equal to E, where this is in C, this is in Z, and this is in Z, the Galois group will drop. Okay, so in general, you don't have finitely many. You can think it's I mean, the general structure of the delta special varieties is the main thing that don't know how to do in full generality. So we don't know how to compute them. But in all the examples we will see, you have a countable. Okay, here it's not countable. So you have some subvarieties, but which are somehow indexed by integers and something in C, such that they are the point where the Galois group drops. And here we saw that the Galois group drops correspond to being a proper subgroup here. Okay, is this example a bit helping?
And it means that the solution some algebraic relation side of that, right?
It means that the solutions of the, so we'll see, I will say the theorem and we'll see how they show up in the theorem. Okay, and how they show up in the theorem will explain, I think, a little bit what they are from. And it's in some form like exactly what you said. The theorem says something like exactly what you said.
Can I make a remark?
Yes?
I think a very cheap example is obtained by starting with any connection, let's say that with full Galois group, and then you pull back the connection over a positive map with positive dimensional fibers. Right. Then on the fibers, the Galois group will be trivial. The fibers will be in a section.
Okay.
But
Yeah.
In general, it's much richer. It's not have such nice structure.
Okay, so you say you start with any connection, you take a map to X, you pull back the connection, and then the fibers are delta special. Okay. Yeah, this is related to one of the exercises where the fibers are finite. Yeah. Okay. So the main theorem that I want to explain, which is the theorem A of their paper, it's the same thing. So with the assumption of the setup, assume that G is sparse. So I will describe what sparse means just after the theorem. This is some kind of technical assumption. So you take V, an algebraic variety of V, a closed algebraic subvariety of V, and L, a leaf of delta of nabla.
The first V is a Z or something.
Hmm?
You wrote
Oh, P.
V, the close part of P.
P. Okay. And L, a leaf of delta. And so consider, so assume, so okay, we write it like that, and denote by. So I'm writing very badly, so I'll try to curly V, an irreducible component of the intersection. Okay. And you assume that the dimension of V is smaller than the dimension of this irreducible component of the intersection plus the dimension of your group G. Then the projection of V is contained in the delta special subvariety of X. So let me first comment on why this inequality means and why does it make sense. So what is this inequality means? Okay, so if you take X and Y, algebraic subvarieties, closed algebraic subvariety of P, this one has dimension N, this one has dimension M, and this one has dimension P. So you expect, one expects, in general, the irreducible component of X intersected with Y to have dimension N plus M minus P. Okay, if the intersection is transversal and everything is complete and everything, you expect that you have this kind of dimension. So if we do it here, so similarly, one expects, so dimension of V of the intersection to be what? To be, so the dimension of V plus the dimension of L minus the dimension of P. Okay, but the dimension of L is the same thing as the dimension of X. Okay, because L is a finite covering of X. And dimension of P is dimension of X minus plus dimension of G. So one expects the dimension to be dimension of V minus dimension of G. And so you see that this inequality minus. This is dimension of, there's a minus here. But you see it's the right here, there's a. So if you take the dimension of G on this side, this tells you that the dimension of the intersection is strictly greater than the dimension you would expect. Okay, so if this is too big, okay, if the intersection is too big, then actually something special happens, and something special means that the projection is contained in a delta special subvariety. Okay. Much time do I have left? So G is sparse. Yeah, you're right. So G is sparse means that if you take, if H is a proper Lie subalgebra of the Lie algebra of G, then there exists a proper subgroup. Remember, we also assume that G is connected, right? So proper subgroup have a different Lie algebra than the Lie algebra of G, such that H is included in the Lie algebra of H. So every Lie subalgebra is contained in the Lie algebra of a proper subgroup. Okay, and so they say, so I don't know exactly why, but they say that all semi-simple groups are sparse. Okay, and we will use only for PSL2 of C to the power R. Okay, a non-example is GM to the power R. Okay, that's why we won't recover actually Ax-Schaunel from the exponential from this theorem. Yes, because you can just take a line with irrational coefficient. I mean, with irrational coefficient in the Lie algebra, and the group that you get is Zariski density. So before explaining a bit the proof of the theorem, so I guess I will need to explain something. I want to explain the cases that are trivial. And so I will first make a couple of reductions. And so the last remark is that we may assume that actually V is the Zariski closure of this curly V. Okay, we may assume that V, we take the intersection and we replace V by the Zariski closure of the curly V, and that V is irreducible. Okay. V? Yes. So the Zariski closure. Yeah, you can assume that V is irreducible in the first place. Usually when I say subvariety, I don't assume irreducible. But I mean, if you want to. Okay. Yeah. So I guess that yeah. So I will give you. We'll see when I will describe it with foliation. It's a bit easier, but here I guess there are countably many. There can be countably many irreducible components. Okay. So if I assume this, the conclusion is equivalent to actually proving that P of V is contained in a delta special. And it's also equivalent to P of U is contained in a delta special variety, subvariety, where U is a dense, is a non-empty Zariski open set of V. Okay, so I can work locally on V somehow. Okay, this is just the property that P of A bar is contained in P of A bar. Okay, so denote by V star the smooth locus of V. So I guess if I understood correctly the lecture of yesterday morning, I guess you could take the normalization instead of doing that, but I'm just going to restrict the foliation to V star. Okay, so I'm looking at V star because I want something smooth, and I'm restricting the foliation H delta. Okay. And so V star, so now, okay, is a foliation of rank. What is the rank of this foliation? Okay, this is the dimension of this curly V. Okay, because we assume, I mean, essentially the leaf of this foliation would be this curly V. It's an irreducible component of V intersected with N. Okay. And so this foliation has no rational integrals. And so now what cases are clear? And so two easy cases. is this case of the rank of this foliation is 0. Okay, so if it's a foliation by point, or if the rank of this foliation is actually full rank, the rank of H delta. Okay. So what happens if the rank of this foliation is 0? If the rank of this foliation is 0, this means that curly V is a point. Okay. And so in that case, it's just that every point of X is delta special. It follows from the definition. Okay. So if curly V is a point, the projection is a point, and therefore, in that case where the rank is equal to 0, we have nothing to do.
Is it necessarily of X or maybe of chi of V or something?
Every point of X is delta special. So if you look in the base, when the definition of delta special that I gave, every point is special. So in that case, when you want to prove the theorem here, you want to prove that P of V is included in a delta special subvariety. But if V is a point, P of V is a point, and every point is delta special. Okay. And so if this foliation has maximal rank, this means that actually the variety V you started with is delta invariant. Okay, if your foliation restricts to a foliation of the same rank, it means that your variety is delta invariant. But by definition, we assume that the Galois group is G, which means that the minimal invariant subvarieties, okay, are equal to P itself. Okay, and so here, the fact that Gal of delta is equal to G implies that V is equal to P. And if V is equal to P, this inequality cannot hold. Okay. So in which situation we are? We are in the situation, the interesting case is when this foliation has rank between 1 and the dimension and the rank of H delta minus 1. Okay, these are the interesting cases. H delta restricted to X star has rank. Dim of X. Okay, if you want max of the dimension of V, and dim of X minus 1. Okay, and this, because we assume that V is the Zariski closure of V bar, this always has, so this foliation has no rational integral. And so the proof is to describe what this foliation looks like. Okay, and so to describe what this connection looks like, okay, in the 5 last minutes that I have, okay, I will use it. So to describe what this foliation looks like, we will use something that is known as the connection form. Okay, and for this, I need to recall a couple of things about G-valued one form. And then I will stop here and I finish the proof. I will do the proof actually next time. Okay. So we fix X, so G-valued one form. So there's a canonical way to present a principal connections like that, and this is what I want to explain. And so you have G, a finite dimensional Lie algebra, and X, a smooth algebraic variety. Okay, so G-valued K form is a global section of the OX module, which is omega 1 of x, when you take the tensor with your Lie algebra. Okay, let me take the tensor over. Oh, okay, take it in the right direction. And so the tensor is over Z. Yes. Over C. Okay, so if you pick E1, EP a basis for G, okay, a G-valued one form can be written, you can write omega as the sum from E is equal to 1 to P of omega I EI, where these are one form. When this is K forms. Okay, and now you can do about these forms everything that you're used to do about forms. Omega 1, this is a G-valued K form. The OX module. Yeah. Okay. And so you can do the usual thing you do with one form. You can pull back. Okay. If you take at this definition, you can just define the pullback by taking the pullback of the omega I. You can take the exterior derivative. Okay. You have, if you're given a vector field, you have a Lie derivative. You have an interior product, and they satisfy exactly the same formula. Okay, so you have the same formulas. Let me just check how long I have. 5 minutes. K forms. Oh, yes, yeah, sorry. Okay. Yeah, I will use only one form, but I mean, the computations, I mean, it's just so we have the usual operations from Cartan calculus. So the exterior derivative, which take a K form and produce a K plus 1 form. Okay, we have if D is a vector field on X, we have the concatenation, which takes G-valued K form and associated X minus 1, and we have the Lie derivative, takes G-valued K form and associates something of the same magnitude. Okay, so the main thing is what replaces the wedge product. Okay, and this is what the only thing that is a bit different. And I will define only for one form. So if omega 1 and omega 2 are two one forms with values in G, so we can define a deux form, which will denote like that, omega 1 wedge omega 2, and with a bracket, because it uses both the wedge form and the bracket, which to a vector field V1, V2, vectors V1 and V2, sends to 1/2 of omega 1 applied to V1, omega 2 applied to V2, minus omega 1 applied to V2, omega 2 applied to V1. Okay. So if you write omega 1, 2 like this, okay, just to tell you what it is, omega 1, omega 2. Okay. This is the sum from ijk of constants which are related to this Lie algebra times omega 1 wedge omega 2.
It's the same thing as taking the wedge product. So you end up with two form with coefficients in wedge 2 of G. And then you just do the Lie bracket on the second factor.
And then you just do, so you first go, you take the wedge product of this form one by one,
Yeah.
and then you
Not
do.
one by one, but the wedge product, I think you have a natural map from omega 1 tensor G twice to omega 2 tensor wedge 2 of G, right?
Okay. Well, which,
Okay.
because usually we use the product to define the wedge. Okay. And so the only example, the only thing I want to explain is how this relates a little bit, but the example, the classical example of such a situation is you take G, an algebraic group.
What about K in the sum?
So sum of I, J, A, K of, okay, so if you want, you can write it like that. Okay, so the C, I, J, K are the constant structure of G. So you can write, if you pick a basis of G, you can write, these are called the constant structure of the Lie algebra.
K's are missing. Exactly. That's what the point.
Hmm?
There is a K and there is an EK at the end.
There is a K.
Then a EK.
And then you have to put the EK.
The element
the
of
one
the
here
one.
and
Oh. Yeah, otherwise it doesn't make sense. Okay, and so the point is that if you take an algebraic group and you look at the form from TG to G, okay, which take a vector field on the point G, and what I'm doing is that I'm taking the D, so RG star of V, which is DRG minus 1 of V. So you start with a vector at a point G, then you use RG, which is an isomorphism, to pull it back this vector into the Lie algebra of G, which is a tangent space of G. Okay, and you get a G-valued one form. Okay, is a G-valued one form. Okay, and the integrability condition that will show up everywhere next time. Okay. Satisfying. Okay, so this I will denote omega G. Satisfying that the differential of omega G is omega G with omega G. Okay, and we will use this form, which are present on the fibers of the tangent bundle, to give a canonical way to present the connection of a G principal bundle, and then to compute the foliation induced on the subvarieties of bigger rank. I mean, satisfying the condition I gave before. So I will stop here, and I will finish the proof next time.
Are there any questions for him? Maybe can you explain briefly maybe the last form? I was a bit lost. What's the meaning of this omega G?
Of this form. So this is a canonical form that lives on any algebraic group. Okay, and so in the case where we will be, we have a projection from P to X, and the fibers of this projection are canonical form. And so this is an object which is canonical, and because of that, we will get a one form, which is the same as omega, which goes from the tangent bundle of P over X to G. Okay, so a G-valued one form, which gives a isomorphism at every of the point. Okay, so this is just a way to give a canonical way of finding a G-valued one form on a group G And since it's canonical, we will get it on all principal bundle in this form. And this is what we will be using. Okay, and then the other thing is just calculus, Cartan calculus with one form works with G-valued one form. And this is an integrability condition. This tells you that if you think about this as a tuple of one form, this tells you that this tuple of one form is a sum with coefficient in C of the wedge product of these forms.
Any other questions? No. Okay. Now coffee break till 11 and then we have some follow for the second lecture.